The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon and a very warm welcome to everybody attending this workshop today, organized by Intel in association with Analytics India magazine. Today we are going to understand and learn getting started with Intel optimization for PyTorch. Let's start with a brief background. Intel has been working closely with Facebook, now Meta, to contribute optimizations to the PyTorch community and commits to continuously optimizing PyTorch with future advancements of Intel hardwares. PyTorch brings a modular design with the registration API that allows third parties to extend its functionality. IPEX is such a PyTorch extension library, an open source project maintained by Intel and released as part of Intel AI Analytics Toolkit, powered by oneAPI. So this workshop is going to give us a better hands-on understanding of how Intel optimizations are calibrated for PyTorch, installation guide, and performance boost number. In addition, participants will learn about ease of use Python API, vectorization, parallelism, quantization, operator fusion, constant folding, and more. Before we delve into the session, I would quickly like to tell you all about the oneAPI blogathon contest that we are organizing from March 16 to May 15 of this year, 2022, where we are encouraging participants to create meaningful content with the utmost brevity on given topics such as oneAPI, migrating from CUDA to oneAPI data parallel C++, Intel AI Analytics Toolkit, etc. We will soon be posting the link to register for this blogathon contest over the chat. Hold out for that. Coming back to the session, a few pointers that I would like to mention before we begin. Please sign up on Intel Dev Cloud account, a free development sandbox with access to the latest Intel hardware and oneAPI software, and use the event code oneAPI25March to register and follow the instructions sent through the email. The code will be shared on the chat window soon. So please hurry up and register on Intel Dev Cloud with the event code. Also, join us at the Discord channel for live question and answer during the workshop. Attendees kindly note that the trainers will only be addressing questions on the Discord channel. Please use the link shared in the chat window to move over to the platform and pose your questions there during the workshop. Further, we are also running an exclusive lucky draw contest where 10 lucky participants will get a chance to win an Amazon voucher worth 2,000 rupees each. So stay tuned for the workshop. On that note, I would like to introduce our speakers and trainers for the day. We have with us Ms. Kavita Arur, who is the Developer Marketing Lead APJ at Intel, focusing on developing software solutions for the Asia Pacific market. With her more than 17 years of experience, she drives the developer outreach, engagements, and programs in the areas of GPU, HPC, and AI. Along with her, we have Jing Su, who is the Senior Technical Consulting Engineer, working as an AI specialist in a developer product support and consulting organization within the Intel Software Group, and Aditya Sivaya, the AI Technical Consulting Engineer in Intel Software. With this, I hand over the session to Kavita, the Developer Marketing Manager, APJ at Intel. Over to you, Kavita.
Thank you so much, Anushka, for that wonderful introduction and an outlook about the workshop today. So hi everyone, this is Kavita Arur, and like Anushka mentioned, right, I lead the developer ecosystem for Asia Pacific in Japan at Intel. And I welcome you all to the AI Analytics workshop. Aditya, if you can go to the next slide, please. I'm going to briefly talk about a few developer ecosystem programs in the region. And before I jump into the program for the developers and the ecosystem here in the region, I would basically like to set up some ground rules for all of us to follow here. Like Anushka mentioned, the Intel Dev Cloud access is mandatory for this workshop. We would have theory plus a demo session. So if you are participating in the demo and the hands-on session, I recommend that you start accessing the Dev Cloud and signing up for the account. And I think the moderators here will post the link to how to sign up to Dev Cloud and join us in Discord. We are all working from home, just like you. We are not on site, not in office. So if there's an internet connectivity issue, if there's a glitch on the webinar, go to webinar. Please bear with us, and we'll be back with you very soon. We are taking all the questions only on Discord. Please bear with us, and we have live moderators on Discord just assigned for to help answer, address any of your questions across the content you will learn today. So feel free to join us there and get answers to any questions you might have on Intel oneAPI or the AI Analytics Toolkits. Finally, I would also like to talk about the trivia poll. We have some exciting poll questions for you, and that would be placed as we go through the content for the day. So participate, and it's going to be fun. Yeah. And with this, I would basically talk about few programs that are defined just for the developer ecosystem in the Geo. The very first program is the Intel Innovator Program. The Intel Innovator Program is basically a recognition program for like-minded developers like you and those who are participating here today. As an innovator in the developer ecosystem, you are a top-tier expert who can innovate, who can share your stories on the DevMesh portal. You have free access to Dev Cloud. You have free access to a lot of assets and content within the ecosystem. You also have, you can sign up projects with us under NDA, and there's a lot of networking and opportunity for you with Intel tech folks, as well as the community which is available on DevMesh. I will touch about DevMesh in the next few slides, but as an innovator, you have access to Intel hardware and Intel software. You have ability of the Intel software stack for you to start evolving and innovating with your projects. You can also do early experiments, prototypes, testing, and research with us. And you're on the spotlight, right? So you can share your projects on DevMesh. DevMesh is a community which has about 2,000 plus projects, and they're not just on oneAPI, right? They're on AI. You need many technology, whether it's game dev, AR, VR, or IoT. If you are a developer in each of these segments, go ahead and explore DevMesh, and you will be amazed to see the amount of projects which are available there. So you can share your projects in DevMesh. You can also curate articles. So like I think Anushka just talked about the blogathon contest, right? So go ahead, participate, register there, and sign up and write some amazing content on oneAPI. And how have you evolved with the technologies? What are the projects you're working on? So write a story about oneAPI through the blogathon contest. We have a lot of media activities happening, so you can be a spokesperson there. You can come and share your projects there. We can amplify your project. We can also amplify your content. And finally, there's a lot of speakership opportunity, for you, not just in workshops like this. We also do very large-scale conferences. We do summits across the year. So in our summits, we usually invite our certified instructors and our innovators to come and share their projects. So it's a huge momentum for you and for us. It's a win-win collaboration for you to share your research work. With this, I would like to introduce my the next program we have for the developer ecosystem. And these are basically the technology partners. If you're a company who is already into the technology business of consulting and selling and addressing the technical needs of developers, if you're someone who's trying to meet business challenges, trying to address business challenges and issues and developers in the field, right? This role is for you. So come ahead and join us. We have roughly about 19 to 20 companies across 10 countries today who are our tech partners. They basically call us oneAPI technology partners. And there are certain level of expertise we look right? If you're a background of parallel programming for CPU and GPU, if you're already into the consulting business, and of course, provided you get the training and assessment done within Intel, you have opportunity to come and join this partner program with us. And the next program that I'm going to talk about is about the Certified Instructor Program. And Aditya, if you can jump to the next slide, please. Yeah, the instructor program, again, is like the innovator program. It's a recognition program. There are certifications just for the oneAPI program. You need to pass the certifications, get trained yourself on the certification. And then, you can endorse Intel oneAPI. So you are like a leader for us in the market, in the geo, where you go and train the other developers. You become an evangelist with us. So you become an Intel evangelist who can go and support these workshops, these meetups. and start curating content at the same time training fellow developers who can learn and explore on Intel technologies. So we roughly have about 64 such instructors in the ecosystem, and this has like been a span of few years, right? We started this, so we're growing and evolving. And if you want to sign up for this, reach out to me on Discord, and we can get you onboarded on the certified instructor program. Plus, there are a lot of other benefits you can explore once you come in. And finally, I'm going to touch upon the other few programs we have. So the next slide, Aditya. If you're still not ready with all of this, you have Intel DevCloud, and that's what we were just talking about in the very first slide. DevCloud is mandatory for this session, but it's a free sandbox toolkit for you. No installations or no configuration steps required. You have 120 days of access. If you need access beyond 120 days, you can send out an email to us saying that, hey, I'm working on a specific project, and then you get beyond that 120 days of free access, right? You can still work on your projects and code out there. There are also a lot of DBC++ and SQL related training programs available on Intel Developer Zone. Go and explore your self-paced learnings there. And finally, DevMesh, right? Arita, if you can go to the next slide, please. So DevMesh is a core hub for content. So like I mentioned earlier, we have about more than 2,000 plus projects readily available for you to see, explore, innovate with those projects, right? And start curating your own projects and thoughts. So what we're expecting here is, come up with an idea, conceptualize that idea, use Intel technologies to prototype or come up with a proof of concepts and share these on DevMesh. You can also be in an NDA with us if you're an Intel innovator. You have a very huge networking opportunity on the DevMesh site. You can reach out to your fellow developers, your community. There are there are beginner level developers, there are experienced and senior developers who can actually evolve and help you in bridging up this gap. So come and explore devmesh.intel.com with us. I think that's pretty much what I wanted to cover for this session. We have a survey, so we would like to hear more from you at the end of the session, and we will facilitate, share this on Discord and on the GoToWebinar. And we have the blogathon contest running. There are a lot of exciting prizes to be won, so sign up for that. With this, I'll hand over the session to Aditya, and thank you so much for listening to me. Aditya, over to you.
Hello, can you hear me?
Yeah, I can hear you.
Yeah, thank you, Kavita, for introducing us. So my name is Aditya, and I'll first start with the agenda for today's workshop. So first, I'll be talking about the oneAPI Analytics Toolkit overview, and I'll also cover one demo for machine learning optimization done by this AI Analytics Toolkit. So, and then I'll hand it over to Zing. He'll cover the Intel optimization for PyTorch introduction, and then one case study, and then he'll do the hands-on demo for Intel optimization for PyTorch. So let's start with oneAPI toolkit, because this. So I'll cover like one or two files for oneAPI, because this is the base for our AI analytics toolkit. So basically, oneAPI is a unified programming model to simplify development across diverse architectures. So diverse architectures I'm talking about are these CPU, GPU, or FPGA, or any other accelerators. So we call them XPUs. So if we have some workload which is intended for CPU, let's say, and we want to port it to GPU or any other architecture, then we need to do some kind of code changes and we need to put some effort. So to eliminate that effort, we have this cross-architectural language for all these XPUs, which will like reduce that effort, and that's what we call, that's what comes under this oneAPI. So basically, oneAPI is a developer interface to all these XPUs, giving users the ability to parallelization and to get the parallelization and optimization from Intel software under one product. So one API is like this, and it has some libraries which will optimize our frameworks like AI frameworks and many other frameworks. And it has some languages like Intel distribution of Python, and then some compatibility tools. Then it also has some tools like analysis tool, and then debug tools. We'll talk about these later in few slides. Mm. So this is the structure of one API toolkit. Basically, it has one base toolkit, which will be which will be there in all the domain specific toolkits. So we have various domain specific toolkit. Like for AI, we have AI analytics toolkit and Intel distribution of OpenVINO toolkit. So all these domain specific toolkits use this one API based toolkit under the hood to optimize our let's talk about. So this is our one API based toolkit. So it has all these libraries, API based programming libraries, and it has direct and then it also has the profiling tools. So in the AI based programming, we have these four libraries which will be like powering our one API analytics toolkit. So first is this one API MKL, one MKL. So this is basically optimizes our math operations and linear algebra operations for Intel hardware. And then we have one DAL, which is responsible for optimizing our machine learning algorithms. And we have this one CCL. This is basically responsible for distributed training of deep learning models. And one last one, which is one DNN. This is the big backbone for all web. This is basically responsible for optimizing all the AI frameworks like TensorFlow, PyTorch, and many other AI frameworks. And in the base toolkit, we also have this Intel distribution of Python. So in this one, we have most of the machine learning library optimized by this toolkit. Then we also have these uh, analysis and debugger tools. So this VTune is like a profiling tool which will like tell us what's going in our code, and which part of the code is taking like more memory or CPU. So this will help optimize our code better. So this was the introduction to one API based toolkit. Now let's come to AI analytics toolkit. So in AI analytics toolkit, we have deep learning part, and then machine learning and data analytics, and also core Python, because Python Intel distribution of Python is also there in this. So in deep learning, we have Intel optimization for TensorFlow and Intel optimized PyTorch, and then Model Zoo. So in Model Zoo, we have various deep learning models which are like optimized for Intel hardware for like benchmarking purpose. And then we have this low precision optimization tool, which will convert our full precision model to a low precision to get faster inference. Then we have this machine learning libraries optimized. So Intel optimized scikit-learn and XGBoost. Then for data analytics, we have Intel distribution of Python, which is like a optimization, replacement for pandas, and it takes advantage of OmniSci backend. And in core Python, we have Intel optimized NumPy, SciPy, and Numba, and Pandas, and data parallel Python. Now let's come to this AI software stack for Intel XPUs. So basically, this will give a brief about all the AI software stack we have. So let's start from the bottom. So if we have for every laptop or cloud or edge, we can easily use the AI analytics toolkits. Let's say we have a laptop or workstation, we can just install the AI analytics toolkit on it's available for Linux or Windows or Mac OS. So for every OS, it's easily installable. And similarly on cloud like AWS or Azure or Google Cloud, we can like install the toolkits, or even easier way is just use the Docker containers. So Intel has its own repo for on Docker Hub. Like it has all the Intel optimized versions of frameworks over there. So you can just download that image and get started with the toolkit on the server or cloud. So there is another platform like MLOps based platform, Converge.io. It also has all these Intel optimized frameworks images on it, and it also provides various templates, hardware templates. So you can just do the benchmarking on latest hardwares from Intel on Converge.io. Then on edge, like we have various tools. If we have some workload and we want to run it on edge, we have these two tools like this INC and OpenVINO toolkit. So what INC will do is if we have some AI workload and it will convert and it will basically compress our workload into one small application that will be easy to use on edge devices. So this is our structure, and we have all these four libraries: one DAL, one DNN, one CCL, and MKL. So these will basically power our most of these AI frameworks and libraries. And then we have this Big DL. So Big DL is basically distributed deep learning framework for Apache Spark, and it helps data scientists and data engineers to build end-to-end distributed AI applications. So this was a little brief, and let me talk about this SIGOP. So we have this data analytics libraries here, and then we also have these optimized frameworks. Then optimize and deploy in models, we have this SIGOP tool. So it is basically used for hyperparameter tuning. It will basically reduce our effort to find the best hyperparameters for our model, like machine learning or deep learning model. And then we have this INC, which basically converts our full precision model to low precision. Okay. So that will make our inference faster. Similarly, the OpenVINO toolkit, it's basically this is the toolkit for deep learning inference. It will it's very easy to use, and it's basically mainly for used for edge devices. So let's talk about the OneDAL library. So this library is basically for machine learning algorithms optimization. So this is basically optimized. This has optimized building blocks for all stages of deep data analytics on Intel architecture. So if we see this data analytics pipeline, in this we can broadly classify it into two categories. One is like this pre-processing and transformation into one, and then last four in other. So first two needs this NumPy and Pandas, all these are required for this. And then so these are already optimized under OneDAL, and last four, these are optimized with scikit-learn and XGBoost. And so what makes OneDAL faster? So it already has this one LKL optimization, which will make our math operations and linear algebra operations faster. And then with threading, what it will do is it will utilize all the cores in the CPU. And then with advanced vectorizations on latest hardwares, it will also again it will improve more, and it also optimizes our memory usage. And in the end, we can also use multiple nodes to scale out on various nodes. So we have these four components in one DAL: NumPy, Pandas, and sklearn, and Apache Spark and XGBoost. So I'll talk about sklearn because this is the one of the like most important machine learning library used. So I'll cover Intel extension for scikit-learn, and I'll also show one demo for this. So Intel extension for scikit-learn, basically how we can use this, I'll cover that in this. So if we have this normal scikit-learn code, let's say we are doing sklearn.svm. So we are taking this SVM algorithm and using it. And to use this Intel extension, what we need to do is only we just need to add these two lines like from sklearnx import patch sklearn. So it basically it basically add this patch uh, of optimized version of sklearn into our code. So what and remaining things are very same. You can just see nothing is changed. So this is the change only we need to do. And once we are done with our Intel optimized version of sklearn, we can just unpatch this. And this Intel extension for scikit-learn can also be like installed on pip or conda also directly without using AI analytics toolkit. And if we don't want to change the code, we can also use this on command line like Python -m and then sklearn next. So it will automatically activate our Intel extension. Uh, so this is the benchmark available. So for this Intel Xeon Platinum hardware, like CPU, what we have done is like these are the results we can see. So for different algorithms, we can see like if we either it's a training or like inference or like prediction, we can see like very good benefit with the Intel optimization for scikit-learn. Uh, so can we see the first poll question, Anushka? After this, I'll show the demo.
Yes, sure.
So the question is like which components are currently included in the AI analytics toolkit. I can't see the answers. Okay.
Aditya, are you able to see the poll?
Not on my screen. I think like in
Look at your
audience view,
control
I can
panel.
see, but for me,
Yeah, on the control panel, it says
yeah,
poll in progress.
audience.
On the screen, I can see it, so the audience are able to see it. But you know, it's analyzing the poll. I think it's collecting the responses. And can you see it on the control panel?
Yeah, I can share
No.
results with you if you want.
Yeah, once
Yeah.
you close.
I think the poll is still going on. So let's wait for another minute and 20 seconds, and then we can share the poll results with everybody.
Sure, thank you.
Okay. Yeah, I can see the results in audience view. So yeah, I think most of people have given the correct answer. So we can, as I showed, Intel optimized TensorFlow and Intel optimized PyTorch, both are already available in AI Analytics Toolkit, and this Intel distribution of Python is available in base toolkit. So it will come with all the domain specific toolkit. So the answer will be like all of the above. So let me now come to the depth cloud setup part and the demo part. So so if everyone so if you have not done the depth cloud setup, then you can just uh, do right now with me. Okay. So first, you need to do what you need to do is just open this link. I think I can paste this link. Kavita, did we share this link with everyone, or should I copy paste?
Yeah, the DevCloud sign up link is on the chat window as well as on Discord.
Okay. Let me also share again. So once you open that link, uh, I so once you open that link, you should fill this form first, the name and all, and then more about you, and then terms and conditions. Once you fill this form and submit, you will receive one email. Mm. So once you submit this form, you'll receive one email from Intel Dev Cloud account confirmation, with this title subject, and you need to click on this verify your email, and you'll be able to you'll reach to one of the pages where you can just sign in with the credentials you used. Once you log in there, uh, let me show it like you can just so let me you can go to this link. So I wanted to share this link with the Ken. How I don't see any option to everyone.
I have sent out the DevCloud link, but
So once we
can you
open
send
that,
it to me? Yeah, the get started, right? Let me post this on. So
so
let me post this, Aditya. I'm sharing this with the audience.
okay. So once you sign in, let me show the process. Once you sign in, you can just click on this working with one API, and it will open this page. Basically, it will open this page, and here we need to click on this get started. And on get started, we go to the bottom, just launch uh, Jupyter Lab.
Aditya, do you want to do a quick hand raise of how many people have gone to the step one? And
Okay. So, mm, countries. So can we see like how many of you like attendees have already registered for DevCloud? Like a hand raise, mm, or like with me at this point. Mm,
I could guess about 25 hand raises there.
Okay. Uh, what I was asking, like, did we share that link, like sign up link, like?
Yes, yes. Yes, Aditya, it's on the Discord as well as on the chat window.
Okay, okay. So if you have not done it, just click on this link and fill this short form and just submit, and you'll receive one email where you can just verify your email, and you are good to go. Like just you just need to go to the right page. So the right page I already showed you is so once you sign in, you can just click on this working with one API, and once you click on it, just click on this get started, and once you click on this get started, you will just go to the bottom and launch this Jupyter Lab. So that's where like our Jupyter environment comes, and we'll do everything there. So once you click on the launch Jupyter Lab, we'll see this kind of interface. And here I wanted to show one quick demo for SK Scikit-learn, uh, Intel extension for Scikit-learn. So if you can see my screen, this is a demo for like KNN algorithm, which is like already with Scikit-learn. Uh, and the data set here is MNIST data set, 110 digits. So what we are doing is basically first we'll import all the sklearn important like sklearn libraries, and then we'll fetch the data set like MNIST data set. Uh, it might take some time because it's downloading the full data set. So this demo is like for like this is I am showing this like I am showing this demo, but you can try it on your own later. I'll share the steps. So let me convert these to uh, like to test and train, and then here is what we are doing the we'll adding the patch. So from sklearnx import patch sklearn and then patch. So here it will activate our Intel extension for Scikit-learn. Now here just we'll train our model. So we have the parameters and fit our model to train data set. And we can see it took 4.68 seconds. Here we'll see the report like for F1 score and all accuracy measures. Now what we'll do is we'll run this model fitting with like without Intel extension. So we are unpatching it here, and then I'll run this again without Intel extension. So the code is same, like totally same. We didn't do anything, just we unpatched this. Here it took like 21 seconds. As we can see, like over there it took 4 seconds, and here it took 21 seconds. And we'll compare the accuracy first because we don't want to lose our accuracy, like model's accuracy. So all these are like very same. You can see 0.96 and 0.96. So we can see like there is no loss of accuracy, and we can see like 4.5 of 5x of speed up with Intel optimization for scikit-learn. So that's what the demo is like. We just need to install the Intel extension for scikit-learn and just add this patch, and it will give you the speed up. And it like the speed up depends on like what hardware you are using. So it can go up or down depending on the hardware and then the use case or algorithm. So after this, I think my demo is completed, and now for Intel optimization for PyTorch, I wanted to set up uh, like an environment. Basically, this I am setting up this environment because it will take some time, and you can do this now. And Jing will show the demo for this, like hands-on for this. So so for PyTorch hands-on session, what you need to do is just click on this like new launcher, and once you click on the new launcher, you can just click this terminal, and on terminal you need to put this command like so this is like git cloning one of the I think I already have it, but you just need to click on this. Let me share this command first. um, so once you git clone this, next step is like create a conda environment like for a PyTorch experiment. uh, so it will create an environment and install Python 3.8. And once the environment is created, just need to activate it. So now it's activated, and now we'll install PyTorch and Intel optimization for PyTorch. and I think it already installed the PyTorch latest version. Now I'll install the Intel uh, optimization, Intel extension for PyTorch. Okay, I think Intel extension for PyTorch is also installed. Now I need to just install this JMLOC. So once all these steps are done, like you have already set up your environment for Intel optimization for PyTorch demo or hands-on. So these steps I'll try to share on chat. Uh, Now I think I should get back to the poll question. So Anushka, can you show another like next poll question? So the question is like which one API library is used in Intel extension for scikit-learn? So the options are like one DAL or one DNN or both of these or none of these.
We're seeing that 52% have voted so far. Attendees, you can see the poll on your screen to attempt it.
Yeah, we can like stop the poll, I think. Uh, yeah, I can see. I think 39% answered one DAL and then 39 both of these. So the answer will be like one DAL because this is like responsible for Intel extension for scikit-learn. One DNN is for deep learning AI framework optimization. So it should be like one DAL. So I'll hand over the presentation to Zing now. Uh, Let me.
Yeah, I can share my screen now.
Yeah.
Yeah, can you see my screen?
Yes, Zing, I can see.
Oh, okay. Yeah. So yeah, good afternoon, everyone. My name is Jin, and in today's session, I would like to introduce you the Intel optimization for PyTorch. So what Intel has done to optimize, to raise the performance of PyTorch. Here is the key feature, and so this is the chart of Intel optimization for PyTorch. Basically, we optimize the PyTorch. We make the PyTorch running on Intel Xeon CPUs, Intel CPUs, and Intel Xe platforms with better performance. So from the low-level library support perspective, we have the oneDNN and oneCCL. We utilize these two libraries to optimize the performance of PyTorch on Intel hardwares. So oneDNN is the library that Intel designed specifically to accelerate the performance of popular deep neural network operations like convolution, pooling, matrix multiplication, this kind of operations. And oneCCL is the library that we designed to accelerate the communications between among multiple nodes when we are doing the distributed training. So based on these two libraries, we optimize the framework. We have this framework level. There are two ways that we are going. One way is to contribute code directly to PyTorch, to upstream PyTorch. So we are collaborating with Facebook, now the Meta, to optimize Facebook on Intel platforms. And another way that we are going is to develop the extension, Intel extension for PyTorch. So this is positioned as an extension of PyTorch. So it runs based on PyTorch and loaded dynamically. So based on this Intel optimizations for the framework level, we utilize our optimizations to accelerate the models, the topologies available in several famous ecosystem packages like Torch Vision, Hugging Face, the NLP topologies, PyTorch Lightning. We are working on enabling this PyTorch Lightning with PyTorch. And also we have contributed our Intel extension for PyTorch to accelerate the performance when users use the Torch serve to deliver their applications. So we have actually three major optimization methodologies that we take to speed up the performance of PyTorch. So first is we have the general performance optimization and Intel new feature enabling in PyTorch upstream. And another one is that we have the additional performance boost and early adoption of relatively more aggressive optimizations through Intel extension for PyTorch. So there are three major methodologies that we use to do the optimization. One is the operator level optimization. In this domain, we utilize the vectorization, the parallelization of Intel techniques to maximize the CPU usage efficiency on Intel platforms. And also we use the memory layout optimization methodology, as well as the low precision data types to accelerate the operators. From the model level optimization, we have the graph optimization. So we do fusion to operators to make the topology formed with less operators. And also we apply the constant folding methodology to reduce the overheads, let's say to reduce the operator executed. So this is the graph optimization methodology. And also the third methodology is the runtime extension. So we can, in some scenarios, we need to run multiple streams, multiple instances at the same time. So in this kind, to meet the requirements of this kind of scenarios, we developed this runtime extension to apply the thread affinity to CPU cores and also to their memory allocations. So I will expand this and explain the three parts in detail. We are, so as I introduced just now, we are upstreaming our optimizations to PyTorch. So we start from the Skylake's optimization and then applied oneDNN, and then from the Cascade Lake, we can utilize the VNNI instruction set to accelerate the performance of int8 quantization. And then later from the Cooper Lake, we have this bflow16 optimizations merged. And then from Ice Lake, VNNI, and the next generation, we have AMX. So for the Intel extension for PyTorch, we accelerate the performance further based on the stock PyTorch. We did some experiments with several topologies, which are used, which are very popular. So the performance boost that we got is from 1.08x to 1.71x. And also we have open sourced, published this performance number out in our tutorial web page. To introduce the Intel extension for PyTorch in high level, this is an extension that extends the PyTorch with optimizations for extra performance boost on Intel hardware. And we have open sourced the Intel extension for PyTorch to GitHub. We optimized the operators and the kernels. So the optimized operators and kernels are registered through the PyTorch default dispatching mechanism. And this extension is loaded dynamically in the PyTorch, in the Python script. So what you need to do is just import Intel extension for PyTorch and this library. This extension will be loaded at that time. We not only make it works with Python script, but also we make it working with the C++ executables. So if you are familiar with Python, PyTorch, I think you know that PyTorch has a package called libtorch, which is the pure C++ library designed for deployment of the application. So the Intel extension for PyTorch is also working with libtorch for the deployment. We support two modes that are used in PyTorch, which is one is the eager mode. So we optimize the operators and add the customized kernels, and then utilize the vectorization and parallelization to do the optimization. For the graph mode, we have some fusion patterns, and then we optimize the fusion of the graph mode conversion, and so that we provide the further optimizations compared to stock PyTorch. All this information can be found at intel.github.io/intel-extension-4-PyTorch. We have this as the tutorial website for the Intel extension for PyTorch. And also this github.com/intel/extension-4-PyTorch is the GitHub page that we open source our code out. So let's focus on the operator optimization features. Basically, we have these 4 methodologies. One is the vectorization, then the parallelization, then memory layout, and then we utilize the low precision data type to accelerate the performance. So let's introduce the vectorization. We use a very simple example to show this feature. So let's say we have an operation plus operation, so add operation. Let's say z equals a plus b. Z is the float 30. All of this z, a, and b are float 32 data types. So to do this calculation on Intel CPU, we need to take A into a register and then take B into another register, and then put these 2 data into the calculation, the CPU. I mean, the calculation unit, and then return the result A plus B into another register on the CPU, on board the CPU. So as you can see, A, B, and A plus B take only 32-bit on the register, but we have a much longer register. We have much longer registers on board. So if your system support AVX instruction set, then you will have register with 128 bits. So let's say this A, the register that you use to store A actually is 128 bits long. And if you have AVX2 instruction set supported on your system, then the register is 258 bits long. If you have one AVX 512 instruction sets on board your system, then your register is 512-bit long. So we can do a very quick mathematics. For AVX register, one register can contain 4 FP32 data at the same time. For AVX2 instruction set, one register can contain 8 FP32 data at the same time. And for AVX 512, each register can contain 16 FP32 floating, single precision floating data type of data at the same time. So this graph illustrates the register of AVX2. So you can see we have one register ZMM2, which contains 8 float 32 data at the same time. So we can fully utilize this register length and then do the addition computation. With one instruction executed, we compute 8 pairs of data. So we raised the performance by 8 times. So this is the called vectorization technique on Intel CPU. For parallelization, this is mainly focused on the multi-threads. So let's say we have a master thread contains 3 regions. Inside each region, the task A, B, C, or A, B, C, D, or A, B, they are independent to each other. So we traditionally, if we use the single thread, then we have to wait for A to finish and then execute B. But if we use the parallelization technique, then inside each of these parallel task regions, we can make execution of A, B, C, or A, B, C, D, or A, B in parallel. So they can be run at the same time. Then the length of this parallel task region relies on the slowest execution of one kernel. So we utilize the oneMP as the multi-thread library that default in PyTorch. Okay. The next methodology is the memory layout. Suppose we have an RGB image which contains contains RGB channels. This image is 2 by 2. Then we actually have 12 pixels, right? So at position 0, we have a pixel for red channel, we have pixel for green channel, and pixel for blue channel. So there are 2 methodologies that we can use to store this RGB image in memory. One is called the NCHW. So the last channel is saved first. So if we use NCHW, then the C channel, the color channel, is saved last, and we save the width first. So the memory layout would be, we save 0, 1, 2, 3 for red channel, and then 0, 1, 2, 3 for green channel, and then 0, 2, 3 for the blue channel. Alternatively, another methodology that we can use is called the NHWC, which save the color channel first and then the spatial channel. So in NHWC, we save the red pixel at position 0, and then green channel, the green pixel at position 0, and then blue pixel at position 0, and then RGB for 1, RGB for 2, RGB for 3. So this is basically used in the vision workloads. Currently in PyTorch, the default memory layout is this NCHW. So we save the spatial pixels first. The format in PyTorch is called torch.contiguous format. But because the we can optimize the performance by utilizing the vectorization if we take the color channel first. So the NHWC is comparing to the NCHW. NHWC is more friendly to Intel platforms. We have upstreamed our feature of NHWC to the Facebook, to stock PyTorch. And also we are continuing to upload more NHWC features to PyTorch to make it have good performance out of box. So it is a working in progress feature of PyTorch. Currently in PyTorch, its data type is called the torch.channels last. So if you use PyTorch to use channel last, then you can define an input, define a model, and then use this to function. So input equals input to memory format equals torch dot channels lost. And also you need to put the model to this channel lost format to get better performance with the vision workloads. Then let's move to the low precision data type optimization for bfloat 16. For float 32, this is the definition of how the single precision data type data is stored in memory. We have a leading signature and sign bit to indicate whether this data is a positive data or a negative data, and then followed by this 8-bit exponential part, and followed by 23 bits of the integer part. But in practice, we found that if we reduce this FP32 data into half, then we can have the exactly same length of exponential part, but cut the integer part to 7 bits. By utilizing this low precision data type, we can save the memory, the memory bandwidth to access data, because we make the data as half size, and also we can accelerate the computation speed with this low precision data types. To make it as a native support with this low precision data type bfloat 16, we add a new instruction set to our platforms, to AVX 512, which is called the VDPBF 16PS. So this is there are three instructions added to accelerate the bfloat 16 calculation. So with these three instructions, we can implement the computation of bfloat 16 computation into one single cycle. So this can accelerate the performance a lot. So there are there are several so nature character, according to the nature character of low precision data type, there are some drawbacks of this low precision, because it might invoke some accuracy loss. To address this problem, we introduced two features in the Intel extension for PyTorch: the auto mix precision and split SGD. To use the bfloat 16 API, it is very simple. So first, we need to define a model like the normal usage of PyTorch. So define a simple net, and it is consisted with one convolution 2D. Then, if we do the inference work in imperative path, then we define the model, instance the model, and then define a data, and then we call this. We put the inference code inside the with torch.cpu.amp.autocast scope. So with inside this autocast scope, Intel extension for PyTorch the PyTorch will automatically detect which operator can be converted to bfloat 16, which operator needs to stay with float 32, and then apply its best performance while keeping the accuracy. If you are running in the torch script path, then still the same. Run the torch.jit.trace and torch.jit.phrase, and the inference code with inside this torch.cpu.amp.autocast. The only code change for using the bflow16 is using this with.torch.cpu.amp.autocast. So another low precision data type is called int8. So it is approximation methodology to do the quantization and the process of mapping the values from a large set like float32 to those of the smaller set like bflow16 and int8. This is called the quantization. So int8 is defined as this: 7 bits for the data, int8 data. So for VNNI, we also have specific instructions to accelerate the performance of int8. These are the instructions to make the computation of int8 calculation in finish in 1 cycle. Also, from the next generation of Intel Xeon scalable processor, we have the AMX, which also accelerates the computation of int8. Some calibration features are enabled in Intel extension for PyTorch to tune the accuracy, like this metric methodology, the per tensor, the per channel calibration methodology. Utilizing of int8 in Intel extension for PyTorch is also easy. There are several categories that we need to cover. First is how you calibrate your model, and then how do you quantize the model. And then the right side is how you deploy your quantized model. So the calibration involves 4 steps. One is you need to apply the batch norm folding with, this is the, we need to use the feature of PyTorch FX optimization. So we use this optimization.fuse to apply this function on the model. And then we define a configuration of Intel extension for PyTorch quantization. And then we loop through the data and make the inference function call with inside the apex.quantization.calibrate conf, this scope. So after the 3rd step finishes, we will have the calibrated data inside this conf object. And then we can save this conf object into a JSON file. So we use this JSON file in the quantization step. So with inside the torch.no grade, we invoke the apex.quantization.convert against the model and put this conf object into this model to apply the data that we collected in the calibration step. And then we return the quantized model, and you can save this quantized model with this model.save. So once you finish the quantization steps, then you can either apply it, deploy it with the on-the-fly conversion, which means you load the JSON file and then do the convert in runtime. Alternatively, you can use the saved quantized model, just load it with the jit.load function, and then apply your input your data into this model. Graph optimization involves the operator fusion. So traditionally, let's use this as an example. So A multiplied with B plus C equals R. By default, it will involve 2 for loops. The first for loop works on the multiplication, and the second for loop works on the addition. We can merge these two for loops together. So inside one for loop, we do both the multiplication and the addition. So this is the the illustration of operator fusion. So by utilizing this methodology, we can fuse the convolution to ReLU to sum. So we have a predefined set of operator fusions. Another methodology that we use is called the constant folding. So let's use a binary folding as an example. So the binary here means the addition operation or subscription or multiplication or division. We have one convolution. This is the formula of convolution: y equals weight multiplied with weight matrix multiplied with the input data matrix plus a bias. And we want to fold this with an addition or multiplication. So y dash equals y plus beta, or y dash equals y multiplied with beta. Then mathematically, y dash equals y plus beta, and then we just put this into this convolution matrix. So y dash equals w. So we replace this y with this formula, convolution formula. So y dash equals w multiplied with w by x plus bias, and then plus this beta. So we can see that this bias and this beta is actually another constant. Both of these two are constant. So the result of addition of these two constant values is another constant. So the combination of these two operators becomes another convolution. So y dash equals w dash by x plus b dash. So w dash here is the w, b dash here is b plus beta. The same as for the multiplication. Then let's introduce a little bit for the runtime extension. Natively, the CPU uses Linux tool of NUMA control to implement the functionality of this thread affinity and NUMA well memory allocation. But it has limitations which it fails to control in runtime. So the runtime extension utilizes the thread affinity to enable the control of this thread affinity in runtime. So we provide several API functions for you to use. One is called the runtime, the thread affinity API. So to utilize this feature, you have to use the Intel oneAPI library. Let's define a simple model, and then you can define the CPU pool to put number 1, 2, 3, 4 core, and then inside this apex.cpu.runtime.ping scope, if you run the inference workload, then from this screenshot, you can see that the core 2, 3, 4, 5 are used. Because we count the core from 0. So 1, 2, 3, 4 here is actually the 2, 3, 4, 5. This is one type of API, and we also have the async task API. So again, you define a model and then define two CPU pools. One utilize 0, 1, 2, 3, and CPU pool 2 use 4, 5, 6, 7. So you can invoke this apex.runtime.task against the model, but and also put the CPU pool as the parameter. So task 1 will only use the CPU cores 0, 1, 2, 3, and task 2 will only use the CPU cores 4, 5, 6, 7. So this task 1, task 2, this task 1 and task 2 will return instantly because it is a synchronous task API. So you return the value in Y1 future and this for Y2 future, and then use the get function. This get function will block execution until the task 1 finishes. Okay. This is another module called the multi-stream module. Again, you define a CPU pool. So this module automates all of these operations defined in previous pages. So you only need to invoke this function, API function, against the model, define how many streams that you want to use, and then it will automatically split the task into this number of streams. In this case, we have 16 cores, and we want to run 4 streams. So each stream will only take 4 CPU cores. And if you are input batch size 64, then you will split this module will split the input data into 4 patches automatically. Also, this multi-stream module can do the core binding, the thread binding functionality to reduce the overhead of core traffic. So traditionally, the access might across over several cores, but with inside this multi-stream module, each core will use only its own memory. Okay, please launch the poll 3. Hello?
Anushka, can you please go with the poll 3?
Yeah, the poll is live.
Oh, it's allowed to go. I don't see poll screen yet.
No, it's live. So
Oh, okay.
let me reiterate the question for the audience. Which of the following optimization methodologies is used in Intel extension for PyTorch? The options are operator optimization, graph optimization, runtime extension, or all of the above. Can you please help answer these? Jinxan, there were a few questions posted on the Q&A window here. Do you want to help address some of them? Maybe we can just take about a few minutes to answer some of those questions. Jinxan, are you there? Aditya, do you want to
Okay, I
in?
see that.
Yeah, I lost you there, Jinx, and there are a few questions on the Q&A window. Do you want to help address some of those?
Yeah. Okay. Okay, on the window. Yeah. Question: not able to join Discord. Please go to previous slide. Please go to slide. This is not working.
Yeah, and if anyone wants to specifically unmute, feel free to text it on the Q&A window, and we can unmute you for a few, few minutes, and then we can help address some of your questions.
Yeah.
Please go ahead and
Yeah.
type your question on the Q&A.
Yeah. Okay. So the poll, actually, the poll result, 80%. Yeah, 80% is of people chose the all of above. Yeah, this is the correct uh answer. Yeah. Okay. So
Vincent,
let's
there's a question on Discord, and the question is, please let us know if optimization happens through the dynamic scripts.
the dynamic scripts. Yeah, so basically the optimization works to any of the PyTorch script. The only problem that we'll have for the dynamic script is that it is relatively hard to do the conversion to graph mode. So because it has like if else, right, or the model itself may change according to the input data. So if you do the trace, then you might not get the the exactly full size model of the graph mode. But this is the one uh, the feature of PyTorch. Uh, so we from Intel extension for PyTorch perspective, we can optimize the model that you successfully converted. So does this answer the question?
Okay. Thank you. There's other question, Jinx, and maybe we'll take another minute or so. And the question is there any initiative for introducing quantum computing to solve these problems?
Could you repeat it again?
Are there any initiatives for introducing quantum computing to solve these problems?
Sorry, currently I don't have answer to this question.
Sure. Okay. Please proceed, and we'll answer some questions on Discord. Thank you.
Yeah, sure. Okay. So let's have a quick case study. BERT model is a popular NLP model that we use. So there are several layers of encoder layers, and also it involves the multi-head attention. So this is the attention, multi-head attention, and the structure of BERT. We have several methodologies to optimize the performance of BERT, like utilize the weight per pack, use the in-place softmax to reduce the overhead, and also basically focus on the operator fusion. We can fusion several patterns to speed the performance up. This is the result that we released out for the BERT model on Intel Xeon Ice Lake platform and Cascade Lake platform for FP32 and bflow 16. So we achieve for throughput mode, for real-time inference mode, we achieve at least 1.0 performance gain, and the maximum with bflow 16 is 1.77 times performance times better. So we can utilize the bflow 16 to achieve further performance boost on Intel platforms. We released the Intel extension for PyTorch out, and you can compile it by yourself yourself, or you can install it from the pre-built wheel files. If you want to do compilation, then we prefer you to use GCC 9. And the pre-built wheel files can be run on CentOS 7, Red Hat, Linux 8, Ubuntu 18.04, 20.04, so Ubuntu later than 18.04. We support the Python 3.6 to 3.10 for Intel extension for PyTorch 1.11. We support 3.10. So there are two methodologies, two ways to install. The first step is to install stock PyTorch because we need to run based on PyTorch. And then you can install either the pre-built wheel file or build the Intel extension for PyTorch from source by yourself. We also provide the C++ SDK. First, you need to download the libtorch from pytorch.org, and then download our extension files. So we have the detailed instruction guides inside our tutorial web page. The usage is very simple. It's exactly the same way as the one that you use libtorch. So if you use libtorch, you need to make the CMake list and then use CMake to compile it, and use CMake and make to compile it. So what you need to do with Intel extension for PyTorch is just to replace this find package torch to Intel EXTPT CPU, and then you follow the exactly same flow. We also released the optimized models to Intel AI Model Zoo, so you can get performance out of box, and it covers the use cases of Intel recognition, image recognition, language model, modeling, the object detection, and recommendation. So here is the link for our documentation website, for our GitHub repo, and also we have the contribution guide here. We welcome any contribution from the community to our Intel extension for PyTorch. And also here, this is the link to the Model Zoo. Yeah, let's have a quick poll. Yeah, the question is, what is the low precision int8 inference? A is inference on a poorly trained model, B is inference on a truncated 8-bit integer model, C is inference on a quantized model, and D is inference on a stock deep learning framework. Yeah, so let's review the answer. Actually, the answer should be the inference on quantized model, because we need to do a calibration on a model and then do quantization. So it is not as simple as just truncate the model to 8-bit. Okay, so let's continue to hands-on. Yeah, can I have my screen back? Okay. Yeah, so I suppose you all of you have logged into the Dev Cloud distributor notebook. And you can click this launcher or just click this plus button, and then click this terminal. Then you will get into a terminal. So let's wait for a while. You can get inside this retinonet underscore IPAX folder that you cloned just now. Please make a bash script because we will use the Ice Lake nodes on DevCloud to run this workload. So please write this as a bash file and save it to the folder of this retinonet underscore IPAX. Okay, we have this terminal login. Okay, so we can first use this pb nodes command to check which which nodes that we have on Dev Cloud. So we can see that we have several nodes which has the ICX as the property. So so we can know that this node is the Ice Lake node. And then so have you finished creating this have you finished creating this launch.sh batch script? Please, yeah, so I see some of you haven't finished this. So please make a bash file, a launch bash file, and then copy these contents inside. So you can use Vim, like Vim launch. So cd retina net, what is it? The IPEX, and then Vim launch.sh, and then copy the contents and paste there. Once you once you copy the contents, then you can type this to quit. Please cd into this retinanet underscore IPEX. Okay, then once you have finished creating this bash script, then you can use this qsub command. Still, you need to enter this retinanet IPEX. So inside this folder, you should have a launch.sh and retinanet.py. Then you can run this qsub space. I'll paste this command into this chat window. Make sure run this command in retinanet IPEX folder. So once you execute this command, the dev cloud system will submit this launch script into its backend operating system, and the script will be running on iStack node. So you can see there are two files generated. So this indicates that the execution finished. So we can use this vim command to open, let's say, E. E indicate that error occurred. But if this E file is empty, then it indicates that we got the script executed successfully. So we can open this O launch.sh.o a number, and then you will see that yeah, let's run it again once more. Okay, so we can use this qstat command to see you have submitted this workload to the system, and it is running. R means it is running. So let's wait for those two scripts to show up. Okay, it showed, it finished. Then we can again open this launch.o.
Can we have a quick check of how many people are following this? Can we have hand raisers, please? Maybe you can uncheck your previous. And if you're struggling a bit, maybe you can just write this across on Discord. So I see some hand raises on Discord as well. Can you be specific to your question, please? Jing, I think there are some questions on Discord.
Yeah, I'm seeing that. So yeah, what to do after this Q sub? After Q sub, we can just wait for the execution to finish. You will see two files. So launch.script.launch.sh.e a number and launch.sh.o number. So once you see these two files, then the execution finished. What are other issues? Other questions? Okay, I don't see other questions. So have you seen the execution finished? Okay, yeah. If you see those two types, then the execution finished. So you can use Vim or cat to open the launch.sh.o that file. You told to remove something from. Can you tell? No, from the content of the launch.sh should be the. I will paste the contents once more. Yeah, this is the content of launch.sh. Oh, good to know. Okay, so if you open the file, you will see. Yeah, if you open file, you should see this. Well, embarrassing. I don't have the number here. So you will see this kind of information. It shows the date, the information of your launch, and then this is the end. In the middle, there should have this number printed inside this. So it should look like this. So if you, this is the execution of PyTorch. So inside this retinanet.py, I have added a flag called --ipax. So what this argument parameter do in this script is that here from line 16 to 19. So if this flag is set, then we import Intel extension for PyTorch as IPAX, and then we need to put the model object net to channel last, and then we apply ipax.optimize against this model file, model object. This is the only code change that you need to do to utilize Intel extension for PyTorch. So Once you have finished the execution with Python, PyTorch, stock PyTorch, then you you can change a little bit in this launch.sh. So append the IPACS -- IPACS after the Python retinanet.py. Yeah, exactly. This is what is expected. Yeah, this is good. Yeah, this is the what is expected to show. So if you change the bash script by appending the -- IPACS to the end of Python retinanet.py, and then use that qsub command to launch the execution again, you will see the performance of IPACS. Um, no, no. What you didn't see the Intel extension for PyTorch is because you need to install this. You need to install execute this command in the counter environment to install IPACS. So this launch.sh.o is an output file, so you don't need to edit this file. Have you activate this environment content environment in the launch.py? Okay. Okay. So let me show the yeah. Let me have a quick quick demo on my machine. So it should have similar performance on DevCloud. If we do Retina Net only with PyTorch, then you can see that the cores are used. The right side is exactly the same code that you see in your environment. And then if I run this -- IPACS, so the performance reduced from 557 to 326 FPS, millisecond per frame. Yeah. So yeah, we are over time by 1 minute. So since you already have access to the DevCloud, you are free. Yeah, please feel free to have a play with the IPACS, with running the PyTorch code, running the IPACS code, and also we have a launch script so that you can also take a reference to. How to get UI status? I'm not very clear. What is this question? show the dashboard, show that is qstat. You can use qstat command. Oh, you mean this? This is called the this is called htop command in Linux. So this is not available on dev cloud. It is only available on bare metal machine. On dev cloud, yeah, this is CPU process. Shows CPU process, right? Correct. Okay, so I will also give you some commands that you can try later. The dev cloud, your account should be able to use for 2 years. Actually, I don't have the number, exact number, but you should have at least 1 year access to dev cloud. Oh, okay, 160 days. Yeah, thank you. Oh, sorry. Yeah, correct. Make a correction. It is 120 days. Um, yeah, please feel free to run any projects, any workloads on the dev cloud. So it is fully free, and you can try there on the dev cloud with the PyTorch, with the Intel extension for PyTorch. So if you have your own real-time examples or projects, you can also try there on the dev cloud. Also, we have this model zoo, AI model zoo, so that you can also try the AI model zoo workloads on the dev cloud. Yeah, this is the tutorial web page that we have. We deliver the information of the detailed information of features, installation guides, examples, performance numbers. So everything is here in this the tutorial website. Okay. So yeah, sorry, we are 7 minutes over. Yeah, thank you.
Anushka, are you there? Would you want to summarize and announce the winners?
Yes, let's take that ahead. Just give me a second. All right. Well, that was a great. Thank you, Kavita, Jing, and Aditya, for giving us insight into Intel optimization for PyTorch. I'm sure the attendees had a lot to learn from this session. So thank you so much for the workshop. And let's hear who the winners are for the Lucky Draw contest. Here are the names. Mandeep Suri, Yogesh Gorane, Parikshit Rathod, Rakesh Kumar Tamisetti, Kausalya Veerabhadran, Shubham Soni, Srinivas Chintara, Medha Sharma, Alok Srivastav, and
I think, Anushka, I can't hear you at least.
Can somebody else confirm if I am audible?
Yeah. Now we can hear you, but very feeble.
Oh, is it? All right, just for the sake of, let me just repeat the names again. So I was just thanking our speakers for today, and let me go again over the winners list for the lucky draw contest. The 10 people who are the winners are Mandeep Suri, Yogesh Gorane, Parikshit Rathore, Rakesh Kumar Tamisetti, Kausalya Veerabhadran, Shubham Soni, Srinivas Chintara, Medha Sharma, Alok Srivastav, and Ujjwal Kiran. So I hope all 10 of you are here, and the winners will be gifted an Amazon voucher worth 2,000 rupees each. So congratulations to all of you. And we would like you guys to share your feedback for the session. Please drop in your thoughts on the survey form, the link for which will be shared on the chat window. Now, before we end this session, I would like to quickly remind you all to participate in the oneAPI blogathon contest. The blogathon will be a great opportunity for participants to not only showcase their skills and expertise on Intel oneAPI tools, but also advance their knowledge about Intel oneAPI products and services, as the participant will have to research the subject to gain a deeper understanding. The communication for the blogathon will be conveyed to you separately post the workshop. So that will be all for today. Thank you all for joining us at the workshop. Have a good day.
Thank you,
Thank you.
everyone, for
Have
a
a good
wonderful
day.
session. Thank you. Bye.